Log on, tune in, find out. Another good idea from Cambridge.
Locally homogeneous geometric structures.
Well, I'd like to thank the organizers for inviting me here to speak on the subject. It's always nice to be back here at the Newton Institute. What I'd like to discuss in today's lecture is an attempt to classify geometric structures on manifolds that are modeled on a fixed homogeneous space. So what I'm calling an Ehresmann structure on a manifold will be a geometric structure defined by an atlas of coordinate charts mapping into a fixed homogeneous space. So I'm interested in the general problem of given a topology, loose organization of points, find a way of putting the local geometry of a fixed homogeneous space on that. And in particular, I'd like to be able to describe the classification in terms of a moduli space. The model theory is the theory of Euclidean manifolds or flat Riemannian manifolds. And the point of view that I'd like to take is that I have a pseudogroup structure. So rather than looking at a tensor field or a connection on a manifold, I'd like to choose an atlas of coordinate charts mapping into a homogeneous space such that the coordinate changes from one coordinate patch to another are transformations preserving the geometry. So transformations that arise as restrictions of the transitive Lie group of automorphisms. So a flat Riemannian manifold can be defined that way since every point has a neighborhood which is locally isometric to Euclidean space. So the general problem I'd like to discuss is a moduli problem is to, given a topology and a geometry, find an object whose points correspond to the equivalence classes of these geometries. What I'd like to emphasize in the first part of the talk is that this is quite difficult, and Murphy's law applies. Everything that could go wrong in defining such a space will go wrong. And the subject is really quite rich and has a lot of contact with many areas in mathematics. And so I'd like to describe several examples of this classification problem for topologies sigma and geometries G and X. So the first point is that the space of geometries on a fixed manifold sigma will be described by certain algebraic sets, the character varieties, or things that are locally isomorphic to character varieties. So these will be algebraic sets which are possibly singular with an equivalence relation given by the automorphism of the group, which will be typically an algebraic group, but the action on the algebraic set will usually not be proper and free. So that when one looks at the quotient of the character variety, one doesn't expect to have a nice manifold or variety or Hausdorff space. But then it's even worse because there's a certain automorphism coming from the fixed sigma, the marking. And in general, to get a moduli space, the action of the discrete group, the mapping class group of the surface, in the case that sigma is two-dimensional, will not be a proper action and can be quite chaotic. So I'd like to give some examples of this in this talk. So the talk will consist of a description of the general classification problem. The success story is Euclidean structures, that one has a very good picture of what flat Riemannian metrics are on a manifold. Projective structures and hyperbolic structures have also been very successful, that one has a nice structure. And then a bit of the general theory about forming something that's analogous to the Teichmüller space of complex structures on a surface with an action of the topological symmetries of sigma. If you just look at complete affine connections that are flat and torsion-free on a torus, you get a rather chaotic action of the mapping class group, which shows that the interesting dynamical systems arise from the mapping class group actions, and then describe what's known about representations of surface groups into PSL2R in the classical Teichmuller-Fricke theory there. I'd like to say a little bit about local flexibility and rigidity to show some interesting examples of where the character variety is singular, and then some discussion of what's known about projective structures, and close with an ongoing project for classifying quotients of R3 by discrete groups of affine transformations. So let me begin. The starting point, I think, will be that we want to take this geometric problem of classifying the geometries on a given topological space and reduce it to algebra. And the algebra is through group theory. The geometry will take place on a space of points, that'll be X, upon which a transitive Lie group will be acting. And so this is the point of view that Felix Klein, who was heavily influenced by Sophus Lie, proposed, that a geometry is just the set of objects or entities that are on a space that are invariant under a transitive Lie group action. So that's, just think of that already. Euclidean geometry, the model space is Euclidean space. G is its group of isometries. All the notions like distance, angle, parallelism are preserved. Affine geometry is an extension of that, where we forget about distance and angle, but keep parallelism. So we have a notion, that's just the notion of an affine connection. The group of transformations that preserve parallelism are just compositions of translations with linear maps. So we have a notion of geodesics. These would be parametrized curves of zero acceleration. So I'll describe the classification of affine structures as a basic example of this theory. Projective geometry is an extension where now we complete affine space to projective space, and the group of affine transformations is extended to the group of collineations, PGL n+1R. In that case, the geometric entities that are preserved by projective transformations are the projective lines, which are just completed geodesic straight lines, and the incidence relations between points lying on lines and so forth. So the general problem was first stated by Erisman in 1936. One starts with a smooth manifold with coordinate patches. The charts map into the model space X, and on each component there's a transformation in G that relates the two coordinate systems. So the local geometry of X is transplanted to sigma via this structure. And so this is the notion. I started calling these things Erisman structures, and these things should be distinguished from what are Erisman connections, which are really different objects, even though these structures are special cases of connections, as I'll say in a moment. So the basic problem is, given a topology and a geometry, how can you put the geometry on sigma? So the familiar example is that we don't have a metrically accurate atlas of the world, and therefore the two-sphere has no Euclidean structure. So there are many different ways of proving this fact. On the other hand, the two-torus has a whole moduli space of Euclidean structures. I'll come back to this example later. A Euclidean structure on the two-torus has a well-defined area. If we normalize the area, then we can represent the two-torus as a quotient of as a flat Riemannian or Euclidean manifold, as a quotient of the plane by a lattice of translations. The lattice will mark the lattice, which means we choose a basis of the lattice. By an isometry, we can put the basis in a nice form. The information given by the basis will be a point in the upper half plane. And so the deformation space will be points in the upper half plane. If we change the basis, if we change the marking, that corresponds to the action of the modular group. So the space of Euclidean structures is all say later, is given by one parameter, which is the area, and then a point in the modular curve. So all of this can be interpreted in terms of connections. So this is maybe, okay, so a Euclidean structure would be a flat Riemannian metric. I don't mean to say torsion-free here. An affine structure that I defined earlier is the same as an affine connection, so that's just a connection on the tangent bundle of the manifold, together with the fact that its curvature is 0 and that its torsion is 0. So these are more general than connections on vector bundles, so this is a different subject than gauge theory. The main point is that one gets a connection on a bundle that's related to the tangent bundle, together with some extra information, which in the case of an affine structure is given by the condition that the torsion is 0. So the flat connection that will be arising will essentially be the coordinate changes in the atlas. And there's an extra piece of information that comes from the coordinate charts. And this is a special case of a Cartan connection, which is, again, not strictly speaking a connection in the usual sense, but it's basically a way of modeling the tangent bundle on the tangent space of a homogeneous space. And this will include general Riemannian metrics. There are integrability conditions that are expressed by a curvature object. The structures I'm describing, the Arrowsmod structures, are those for which this curvature object will be 0. And so, as we'll see, the coordinate charts will be given by a section of a certain bundle naturally associated with the structure. The bundle embodies the coordinate changes. And the theory that I want to describe is closely related to gauge theory in the sense that the local deformation theory of geometric structures, of Arrowsmod structures, is given by the local deformation theory of flat connections, and hence representations of the fundamental group. So let me give some examples. So the simplest examples are quotient structures. And this theory properly contains the subject of discrete subgroups of Lie groups. So given any Lie group, one has homogeneous spaces, such as the symmetric space, and then any discrete subgroup will define the quotient by any discrete subgroup, which is torsion-free or generally acts freely on the homogeneous space, will be a manifold modeled on that homogeneous space. So what I'll need to require for the basic examples will be an open subset of the model space with a discrete group action, unless the isotropy group of G acting on X is compact. We need to make the extra assumption that the group is acting properly. So if G is acting isometrically with respect to a Riemannian metric, or more generally on the metric space structure, then knowing that gamma is discrete implies that the gamma acts properly. But in general, one has to assume that. And this is a non-trivial assumption. In that case, the quotient space, they're local slices for the action, which give rise to local coordinate charts, and we obtain a geometric manifold modeled on X, whose covering space is omega, the domain. So interesting and rich class of examples are the convex projective structures, when one takes a convex domain in real projective space and forms a quotient. So hyperbolic geometry is a special case of this, where one takes the interior of a quadric, given 2 points inside the quadric, the interior of the quadric, then the cross ratio, the projective invariant of the 2 points and the 2 boundary points defines a metric, which is the invariant hyperbolic metric on the domain. And every isometry of the hyperbolic plane is realized by a projective transformation, preserving the quadric. So there's just the Klein-Beltrami model of projective space. So there are a lot of a lot of interesting examples of this. Let me give something that's maybe a little bit simpler first. And this is a nice picture that you can draw just with straight edge and pencil. It's projective geometry. This is a projective deformation of the Euclidean 3-3-3 tessellation. So you take the interior of a triangle, that has a natural Euclidean geometry on it, and this is an example of a Coxeter group generated by projective reflections in the sides of one of these triangles. By taking a subgroup of index 6, I believe, one gets a action of a free abelian group of rank 2, and the quotient is going to be a torus with projective structure. You can do this with other discrete groups of hyperbolic motions. For example, here's another triangle group. This is an example which arises in nature, depending on your definition of nature. This is the Weyl group of a Katz-Moody Lie algebra of rank 3 of hyperbolic type. These examples were discovered by Katz and Winberg in 1967, I believe. The domain so here's an example of just an ordinary hyperbolic triangle group. One gets a one-parameter family of deformations. The boundary curve becomes a rather interesting fractal curve. It's C1 and convex, but it's not any better than C1. It's an interesting question to try to compute the Holder exponent of the boundary. And these things form a nice deformation space, as I'll describe later in the talk. Let me describe another example that I'll be coming back to. Here's sigma, the topology. We want to put some geometry on it, so we take, say, an octagon, and then pair the sides by this pattern. When you pair the sides in this pattern, all 8 of the 8 sides collapse down to 4 curves, and the 4 curves all intersect in a common vertex, which is the image of each one of these 8 vertices of the original octagon. And the identification space is a smooth surface of genus 2. So that's the topology side of the picture. We now want to put some geometry on it, so we want to realize this picture geometrically in hyperbolic geometry. And so here's a picture where we're using some sort of hyperbolic graph paper. This is a triangle tessellation. And in this triangle tessellation, we can realize this octagon by a regular octagon with 45-degree angles. The angles should be 45 degrees so that when we go around this vertex, we have 1/8 of a full 2 pi radians of cone angle at that point. And so we can realize these topological identifications isometrically, since all the sides are congruent, and we get a hyperbolic structure on the surface of genus 2. So one can go through and find local charts for the structure based on this identification pattern. Okay, so these are some of the basic examples that I'll come back to in this talk. Let me describe the general theory now. So what I'd like to do is to form a deformation space whose points correspond to the ways of putting the geometry on sigma. And so to do that, I want to fix the topology sigma and then let the geometry vary. So I'll call that M. So M will be a manifold with this coordinate atlas, and it's convenient to work in the smooth category, even though maybe it's a bit of a cheat. So I'll assume that sigma is a smooth manifold, and I have a diffeomorphism. It really should be a homeomorphism or a homotopy equivalence to M. So this is the setup in defining type-Miller space where one takes M to be a Riemann surface, which is not an Ehresmann structure, and a diffeomorphism to fix the coordinates. And now we can impose a natural equivalence relation on these pairs of F and M of isotopy. So we want to say that 2 mark structures are equivalent if the corresponding geometric manifolds are isomorphic as GX manifolds, and the composition of of the marking and the isomorphism is is isotopic to the other marking. Okay, so this is the standard definition of Teichmuller space. Whereby so this is an isomorphism of manifolds, and then we want this diagram to commute up to isotopy. Thank you. Okay. And so the reason for introducing this is that we want to be able to get a nice finite dimensional space. And so, so I'll call that the deformation space. And by composing with automorphisms of sigma, those diffeomorphisms of sigma, so in other words, I'll replace F by F composed phi, then I get an action of the diffeomorphism group of sigma on the deformation space. So this is analogous to the action of the modular group on the upper half plane. And so the space of unmarked structures, the space of structures should really be the set of orbits of the diffeomorphism group acting on the deformation space. And in particular, because this relation of isotopy encodes the includes the identity component of the diffeomorphism group, the action of the diffeomorphism group factors through the mapping class group, the group of isotopy classes. So I'll get this space, which will be, as I will say in a moment, is finite dimensional, with an action of a discrete group on it. And the set of structures should be the set of orbits. Okay, so as I mentioned before, these are closely related to flat connections and representations of the fundamental group. And so let me say a little bit about the character varieties and representation varieties of representations of a discrete group, a finitely generated group, into an algebraic Lie group. So if one considers the set of homomorphisms from the finitely generated group into G, that has a natural structure as an affine algebraic set using the embedding of G inside the general linear group. This structure is invariant is independent of the choice of generators. It's a nice exercise. The coordinates are given by evaluating a representation on the n generators. The natural symmetries of this set are given by the automorphisms of pi acting on the left and the automorphisms of G acting on the right. In particular, the moduli space that's important in differential geometry will be the set of equivalence classes when we quotient by the inner automorphisms of G. I'll say more about this later when I relate this to holonomy. But the space we're really going to be interested in will be the quotient of the affine algebraic set hom pi G by the group of inner automorphisms of G. And I just want to, let me just think of this as a quotient topological space, since this is, it's not really clear to me what the right structure on these spaces should be. And the action of the automorphism group of the source group will factor through the inner automorphisms, and therefore the group of outer automorphisms, which is closely related to the mapping class group, will be acting on this quotient. So maybe I should just mention that I won't say too much about this in this talk, but when pi is the fundamental group of a closed surface, then at least on the set of smooth points quotiented by the set of open subset where the action is proper, this space has a natural symplectic structure. And it's natural in the sense that the that the mapping class group will be preserving that. And so that's the kind of structure that will persist into the geometries as well. So that's the next thing I want to say, is to relate this to the Ehresmann structures. So we can globalize the coordinate charts on the manifold in the following way, that we can think of the atlas of charts as being a map from a disjoint union of the atlas into X, and then the manifold is going to be an identification space, a quotient space by M. That's useful in many considerations, but it's, in this particular case, because the transition functions are locally constant, we can replace this identification with another picture of M, namely as a universal covering space. And by starting with one base coordinate chart, mapping that in by a base coordinate patch, mapping that in by a coordinate chart, then there's a natural extension, sort of an analytic continuation from the base coordinate chart into a map defined on the whole universal covering space. And this is the process of development of Elie Cartan and many others, which gives a globalization of the atlas and a very convenient way of understanding the geometric structure. So this map is a GX map in this category, a morphism, and in such a way that the local geometry on X pulls back to the local geometry of M tilde that's pulled back from the defining structure on M. And so just as the coordinate changes are encoded by a cocycle, a G-valued cocycle on the covering, the coordinate charts in this picture are identified with a representation of the fundamental group in G. And so this is the holonomy representation, just the holonomy of the associated connection. And the action of deck transformations on the universal cover is related by the developing map to the holonomy representation here. And so this is an alternate, more topological global picture of the geometric structure. And so if we look at the collection of all marked structures, the marking gives us a way of identifying the fundamental group. The fundamental group now is fixed, and so we get a well-defined homomorphism. Well, we have a homomorphism from the fundamental group into the Lie group, and it's well-defined up to compositions. So the original choice that we made in forming the developing map, well, any other one is related by composing with a transformation in G. The corresponding holonomy representation is obtained by applying the inner automorphism of G to the representation. So that's just the conjugation by G. And so one can show that the mapping class group, the diffeotopy group of sigma, well, it doesn't quite act on the fundamental group because the fundamental group involves a base point, but changing the base point affects an inner automorphism of the fundamental group, and therefore there's a well-defined homomorphism from the diffeotopy group into the outer automorphism group of the fundamental group, and that homomorphism respects the holonomic mapping. And a basic fact is that when these spaces are given appropriate topologies, so I'm taking the classical topology on this quotient, the quotient topology, the classical topology on this algebraic set over here, and the topology here would be a quotient topology for, say, the C1 topology on the coordinate charts. So when you topologize this space is a local homomorphism. This is a very general fact. We need to assume that sigma is compact for this. That was first noticed and stated in this generality by Thurston. in the 1970s. So all the local geometry of this space will be transplanted back to the deformation space. And in many cases, such as the quotient structures, this map is an embedding. So the space of hyperbolic structures on a surface, the Fricka space of sigma, will be an open subset of the space of representations. And so a precursor of Thurston's general remark is this fact, which was proved by André Weyer in 1960. And the whole point of view is implicit, at least in the work of Ehresmann. And this fact is sometimes called the Ehresmann-Thurston or Ehresmann-Wey-Thurston principle. So local deformations of the geometric structure correspond to local deformations of the representation of the fundamental group. Okay, so let's go back to the familiar example of Euclidean structures. So a closed surface with a Euclidean structure has to be a torus. The deformation space identifies, when we mark the surface, we have an A curve on the surface and a B curve that generate the fundamental group. We can normalize the A curve to be translation by 1. The B curve then corresponds to a point in the upper half plane. And then the area gives an extra invariant, which we can normalize. So the deformation space is the following three manifolds, H2 cross R. The mapping class group that I described is going to be just acting by projective transformations, the usual action on the upper half plane, once we make this identification. So this is a prototype of the kind of classification that I'd like to describe. Well, when we go to a slightly larger geometry, everything goes to hell because the complete affine surfaces are really, the moduli space is basically one point with lots of, it's an uncountable set with a non-Hausdorff topology with no continuous functions on it at all. Kuiper classified the ways of representing, so a complete affine structure means in classical differential geometry terminology, it's a surface with a flat torsion-free affine connection which is geodesically complete. What that means is that the manifold is a quotient of R2 by a discrete group of affine transformations which acts properly and freely. So we're going to classify how the fundamental group acts. So the simplest example would just be Euclidean structures, which are just quotients by lattices, flat tori. And they're all equivalent because up to affine equivalence, any two bases are related by a linear change of basis matrix. So that represents one point in the deformation space. But there are others that are obtained by conjugating the action of the lattice by the following diffeomorphism. This is a simple non-affine polynomial deformation. Its inverse is x minus y squared comma y. And if you conjugate a translation by this diffeomorphism, the effect of conjugating the f inverse and the f cancels out the quadratic term, but what you're left with is the cross term. And this is a nice little calculation to do, that what you have is now an affine transformation that's not a translation. So this is a really simple baby case of what's done in Teichmuller theory when one takes a Fuchsian group and conjugates it by a quasi-conformal homeomorphism to get an inequivalent Fuchsian group. So the topology is the topology is the same. This is a homeomorphism, but the geometry is quite a bit different. So what's the effect of this polynomial change that conjugates one affine group to another? Well, imagine taking a lattice of translations like this one. When you conjugate it, the translations become the level sets, the horizontal lines become parabolas, and the tiling that you get looks something like this. So the lattice I took here contains a horizontal translation, and so we still have horizontal translations. If we take a lattice that contains no horizontal translations, then the tiling now has two pairs of parabolas. Okay, and so this is an easy calculation to do, that these are the only two classes of structures that you get. And Oliver Bowes showed that the deformation space could nicely be parametrized by the plane, and the origin is the Euclidean structure. So you can sort of take an analog by looking at differential forms and writing down sort of a period map to get these coordinates. The mapping class group of the torus is GL2Z, but now the action is not by linear fractional transformations, but it's by linear transformations, the ordinary linear action, and that's a real mess. So if you look at, you have lots of fixed points, the action is ergodic with respect to Euclidean area, and you really don't want to look at the quotient space. So this is one reason that one should look at the marked structures and not the moduli space. So this is a much worse quotient space than the elliptic modular curve. Okay. One of the success stories in this classification theory is hyperbolic geometry. And so the space of hyperbolic structures on a fixed surface sigma is, I'm calling it the Fricka space, to distinguish it from the Teichmuller space, which is the space of marked conformal structures. The complex structures are not Ehresmann structures. They're not given by a pseudo-group of locally constant rigid maps. They're fairly rigid, but not as rigid as a transitive Lie group of acting on a homogeneous space. But the uniformization theorem identifies the space of hyperbolic structures on a surface with the space of complex structures on the surface. I'd like to keep this distinction because it's useful in studying these geometric spaces to impose a complex structure and see how the theory depends on a conformal structure as a parameter. In particular, the Fricka space embeds as a connected component in the space of representations. So here I'll assume that I have a sigma is a closed orientable surface of genus G, and G is PSL2R. And so the openness is the theorem of Weil I described earlier. The closedness is a general fact that discrete embeddings of a discrete group are generally form a closed subset. And then the connectedness was due to Teichmuller and the fact that the space is contractible if the cell is due to Teichmuller using the uniformization theorem, or you just using hyperbolic geometry, I think by Fenchel and Nielsen, or sort of cut and paste hyperbolic geometry. It's known through this work that that the Fricka space is a cell of dimension 6G minus 6, and the action of the mapping class group is properly discontinuous. The quotient is just the moduli space of curves when you identify it via the uniformization theorem. Now, in terms of the geometry, the geometric structure, the representation has a topological invariant associated to it, and that's going to be given by the characteristic class of a fiber bundle over the surface. So from this description of a representation of the fundamental group, there's an associated flat bundle. One takes M cross X, or M tilde cross X, and quotients by the action of the fundamental group. That maps down to M tilde, quotient of M tilde. And then the developing map defines a section. The topological type of this bundle is an invariant of the representation, which in this case is the Euler class. And the work of Milner and Wood actually in this subject is that there's a bound of the Euler class by the Euler characteristic of the surface. Now, the Euler class is the Euler characteristic of the surface when you have a geometric structure, because in that case, the tubular neighborhood of the developing section identifies with the tangent bundle. And that section being transverse is enough to give the coordinate chart. So this is the extra information that one needs when you have a flat connection to give a flat Cartan connection. or geometric structure, and equality is equivalent to having a geometric structure. So the Euler class is a topological invariant characterizing discreteness. And more generally, the connected components of this space are the preimages of the Euler class. So I had proved this around the time of my dissertation using hyperbolic geometry and navigating inside the Lie group PSL2R. In Nigel Hitchens' paper on self-duality equations, he interpreted the flat connections as a certain class of Higgs bundles and obtained the count of the components as well as a description of the topology of the components. In particular, there are 4G minus 3 connected components. And this suggests a theme in this subject that just from this algebraic problem of analyzing the representations, that the geometry and topology of geometric structures might be a useful tool. So let's take that and look for a non-maximal representation. So let's go back to the original geometry, and let's make a mistake. We can obtain, in the same triangle tessellation, we have another tessellation given by regular octagons with 90-degree angles, and we can still get identifications of the sides, realize these identifications geometrically. And now when we build this, we get a hyperbolic structure on a surface, except now there are going to be 8 right angles as we go around this loop. And so this gives rise to a hyperbolic structure with a cone singularity of cone angle 4 pi. And when we remove that singular point, we still get a representation of the fundamental group on the complement. The holonomy around the representation will be a rotation of angle 4 pi, which is still the identity. And you get a representation of the fundamental group of the surface of genus 2. You can think of this as a Riemannian metric with concentrated curvature. So it's a metric space. At the cone point, there's concentrated curvature of an angle of what would be minus 2 pi. And the Euler class can be interpreted as an area, and the Euler class of this representation is going to be the usual Euler characteristic with an adjustment of 1 because of the concentrated curvature. So this representation is one that has, it's not maximal. It has absolute value of the Euler class is 2G minus 3. And in general, one can find hyperbolic structures with cone angles in the other components as an example of representations of the fundamental group in these other components. There's a uniformization theorem for singular conformal structures with cone angles, and due to Mokoyan and Troyanov, the moduli space for singular conformal structures just corresponds to the points where the conformal structure is singular, the cone angles, which is just the kth symmetric power, and then by the uniformization, realize those as hyperbolic structures, and you get representations of this other component. And one way of expressing one of the results in Nigel's paper is that the component, that this map is a homotopy equivalence from this component of the representations into PSL2R with the kth symmetric power. The Teichmuller space corresponds to when k is equal to 0, and then this is just a single point. One theme in the subject is to start with something that we understand, like Riemann surfaces, and try deforming them inside some higher dimensional geometry. And there's a bounded invariant which generalizes the Euler class due to Turayev for the symplectic group and Domingo Toledo for other Hermitian symmetric spaces, and Johann Dupont also in general. The invariant in general will satisfy a Milner-Wood type of inequality bounded by a topological invariant, and equality holds precisely when the representation is this discrete embedding into a group preserving a complex geodesic. So this is a sort of rigidity or stability result based on this sharpness in this Milner-Wood type of inequality. And in general, using the interpretation as a bounded cohomology class, one gets that the representation is a discrete embedding, and this is in a much more general case of a Hermitian symmetric space. And many of these results were also obtained using Higgs bundles and gauge theory through work that we've heard about here by Steve, Oscar, Peter Goth, and Ignacy, and many others. So the gauge theoretic methods are very useful in understanding the topology. The bounded cohomology methods seem to be very useful in understanding the actual structure of the representations. The basic problem is to really try to unite the two approaches. Let me say one thing I find quite interesting about the local rigidity and the interpretation of the Euler class. So again, let's just start with U11 and try deforming that inside the group of isometries of hyperbolic space. So in the case of surface groups or fundamental groups of compact Kähler manifolds, one has a very nice theory, local theory, for the singularities of the space of representations. In particular, there's a natural quadratic, so the Zariski tangent space to the space of representations is the space of one cocycles. This goes back at least to Wei's paper. And the second obstruction class is given by a quadratic form defined on the space of cocycles. And John Milson and I, following an important suggestion of Deligne, proved that the level set of the corresponding quadratic form is a model for the singularity of the space. And what I'd like to describe is a specific example of deforming surface groups in U11 in this way. So we start with a representation in U11, which is essentially SL2R across a circle. And we include that as the stabilizer of a complex line in complex hyperbolic 2 space. And after doing some calculations with the cohomology and the Lie algebras of the relevant groups, one sees that the Zariski tangent space is a vector space, a real vector space of dimension 8 G minus 4. And using the local model for the rigidity, one boils down to looking at a manifold across a quadratic form on an 8G minus 8 dimensional vector space. And the signature of the quadratic form is 4 times the Euler class of the representation. Okay, so this is the Zariski normal space of the U11 representations inside the U21 representations. And the quadratic cone will have signature that's varying. In particular, this identification of the Euler class of the signature is in Ferner-Meyer's thesis. And the Milnor-Wood inequality is just, in this case, can be deduced from the fact that the signature of a quadratic form is bounded by the dimension of the space. And the maximal representations, the ones of maximal signature, correspond to when the quadratic form is definite. So here we have the local representation of a Fuchsian representation of a surface group can be interpreted as the quadratic form defining the normal cone as being positive definite. So the variety looks like x squared plus y squared equals 0. It has no real points, although it's still of higher dimension. And this is an example of where the representation variety has a singularity. So as I mentioned, everything that could go wrong in trying to mimic Teichmüller theory does, and this is a rather dramatic example of where the variety of representations is singular. Okay. So let me describe a few examples, some classical examples, and then conclude with what I think is an interesting classification problem. So the theory of geometric structures modeled on the complex projective line, which I'll call CP1 structures, and the group of projective transformations, so complex linear fractional transformations. These are projective structures. And since PGL2C preserves a complex structure on the complex projective line, any structure modeled on CP1 has an underlying complex structure. And so we could think of these as being projective structures on a fixed Riemann surface. From that point of view, the extra information, the developing map, will now be a holomorphic map into P1, and it's defined up to composition with projective transformations. It's natural to take its Schwarzian derivative, which is a holomorphic quadratic differential. And without very much work, you can show that every holomorphic quadratic differential arises as the Schwarzian of a developing map. And so without really getting your hands dirty with the structure of the Riemann surface, or the projective structure, the deformation space can be identified as a bundle over the Teichmüller space. Teichmüller space, we fix the Riemann surface, and now let the developing map vary. The fibers then identify with holomorphic quadratic differentials. So if you take, it's only an affine bundle. There's no natural choice of zero section. There's no natural holomorphic section. But if you were to take the bundle of holomorphic quadratic differentials over the Riemann surface, you'd get the cotangent bundle of Teichmüller space. Okay. And the good news is that the deformation space is a nice cell, nice Hausdorff manifold. The mapping class group acts properly discontinuously. The actual structures are really quite interesting. So here's a simple example. You take the fundamental domain for a hyperbolic structure like the regular octagon, and now you insert basically a crescent into the developing map, and here's an example of the embedding of the universal cover. So these examples were known to exist by Poincaré. The limit curve here is a very complicated fractal curve that's not even rectifiable and has Hausdorff dimension greater than 1. So there's a lot of complexity that are all embodied in this very nice, almost sort of formal construction of the deformation space that we know everything about. A more complicated example of structures that have been studied recently are real projective structures on surfaces that I mentioned earlier. In that case, the deformation space of convex structures is a cell of dimension 16G minus 16. There's an analogous theory of, so the convex structures are parametrized by a cell. One gets a holomorphic description by associating to every such structure a point in Teichmüller space, a marked Riemann surface. And then the different developing maps are parametrized by a holomorphic cubic differential. And this gives a nice model for the deformation space as a fiber bundle over the Teichmüller space, whose fiber are the holomorphic cubic differentials. So this was understood in terms of Higgs bundles in Nigel's second paper on Higgs bundles, the Lie groups and Teichmüller spaces, where he shows that if you take a hyperbolic structure modeled in SL2R and embed it by the irreducible representation into SLNR and deform it, you get a whole component which is contractible and identifies with a vector space. And Su-Young Choi and I then proved that Nigel's Teichmüller component, in this case for PGL3R, is exactly the deformation space of convex projective structures. One advantage of the Loft and Laborie picture is that now one sees a structure, namely as this holomorphic vector bundle, which is invariant under the mapping class group. And it would be very interesting to understand this for all the other components that Hitchin described in his paper for other split groups. In a different direction, if you look at not necessarily convex structure, Choi in his thesis showed that the arbitrary structure were obtained by a topological construction on this, and the deformation space could be identified with convex structures plus an extra discrete invariant. So one has a complete description of the deformation space here. Okay, so in the remaining few minutes, let me describe what I've been thinking about lately in this connection and another class of geometric structures. So these will be flat, torsion-free, geodesically complete affine connections. So representations of a manifold as a quotient of an affine space by a discrete, properly discontinuous group of affine transformations. A recurrent theme in this subject is that one is really starting always with hyperbolic geometry on surfaces. And there are two types of such manifolds. The ones that were understood and are easily classified are ones for which the fundamental group is solvable. So, for example, one can take any automorphism of a torus, of a Euclidean torus, can be realized affinely, can be realized by a linear transformation in SL2Z, GL2Z. And so the mapping torus can be realized affinely. If that element is an orthogonal transformation, then you get a Euclidean structure, but in general, you just get an affine structure. And these are basically the only types of examples when the fundamental group is assumed to be solvable. However, one can have more complicated examples where the fundamental group is not a solvable group. And in particular, when gamma is a free group of rank greater than or equal to 2. And these can all be related to the theory of hyperbolic geometry on Riemann surfaces. These were classified by David Fried and myself. The solvable ones were classified, and the compact ones were all torus bundles over the circle, but it was quite surprising that these weren't the only ones. And Milner wrote a very interesting, sort of somewhat expository paper about this problem, which had been plagued by mistakes in the literature. Margulis, who was trying to prove Milner's conjecture, couldn't prove the conjecture and instead constructed a counterexample. And that's what I'd like to describe in the remainder of the talk. These counterexamples also have a nice classification and are intimately related to hyperbolic geometry on Riemann surfaces. So what I'm looking at will be a representation into the general linear group, and it turns out that we can reduce to just looking at ones that go into the orthogonal group. So this was part of the classification in dimension 3, that we have a group of orthogonal transformations, and the linear part of the affine representations, the differentials, which are just constant linear maps, are orthogonal transformations in SO2-1, and the translational part is just a vector. And in particular, Jeff Mess showed that the Riemann surface that one gets, the quotient by the linear holonomy, has to be non-compact. So the fundamental group has to be free, which rules out any compact examples, where the three manifolds compact. The cocycle, so the translational part is a cocycle in the group cohomology taking values in R21. That can be identified with the space of infinitesimal deformations of the hyperbolic structure. So the tangent space to the Teichmüller space of this non-compact Riemann surface. And the deformation is one that's characterized by the fact that every geodesic is infinitesimally getting lengthened. One can go backwards. If you take a hyperbolic surface and a deformation of its structure where every curve is getting lengthened, then you get a complete affine 3 manifold with a flat Lorentz metric out of that, which seems particularly mysterious to me. So there are two types of these 3 manifolds, either the torus bundles over the circle or these ones coming from deformations. It's really hard to see, it was really hard to see what these manifolds look like. Todd Drum showed that these things had nice fundamental domains bounded by polyhedra that we called crooked planes. And let me just close with a description of what the deformation space and what these manifolds look like. This is an example of a kind of surface that splits affine space into two pieces and can be used to build fundamental domains for these three manifolds. You can pull them apart. Here's an example of three of them being pulled apart. So the region inside the three manifold, so this corresponds to a three manifold embodying the hyperbolic structure of the surface together with this one jet of a deformation, will look like this region in between. There's the light cone for the Lorentz metric. Sort of, here's the vertex that it goes up. The future's up here. The past is down here. And these two half planes are tangent to the cone. If you take a cross section, you get a tessellation or something like that. Here's the example that you would get by taking the level 2 congruent subgroup of the modular group. So each of these zigzag curves corresponds to the boundary of one of these surfaces bounding a fundamental domain. So the fact that these lines are parallel is an example of the parabolicity of the cusp for this discrete group. So since I've run out of time, let me just quickly say what the deformation theory looks like. We fix the linear part, the hyperbolic structure. So this is like what we were talking about before, where we fix the conformal structure. So we have a bundle over the Teichmuller space, or the Fricka space. It's easily described. The current project, which has a lot of collaborators, is that the fibers of this map, the set of proper affine deformations, are open convex cones defined by length spectrum of the Lorentz metric. And in particular, the case that we've analyzed, when the fundamental group is free of rank 2, or the Euler characteristic is -1, you get 4 components corresponding to the 4 types of the surfaces. And so what we'd like to say is we get fundamental domains that are given by these crooked planes. One knows that the fundamental group is free, and a few months ago in Oxford I was talking to Choi about this, and since then he's come up with a proof in certain cases that the three manifold one gets as a solid handle body. There's a poster that he put up here. Here's the picture of the fibers, which I'll close with. The three surfaces that we have are the three-hole sphere, the one-hole torus, two non-orientable surfaces, a projective plane punctured at 2 points and a Klein bottle punctured at 1 point. The fiber over the Teichmuller space corresponds to deformations that are infinitesimally lengthening every curve. And in the three-hole sphere, that can only happen if the three boundary curves are lengthening. And so one gets a nice picture of a cell, a triangle. Or actually, these are pictures in projective space. So one has a cone. The cone over that is what you should be looking at. This is the case when you don't have any interior simple closed curve. On the two-hole projective plane, you have basically two closed curves, and that gives a four-sided deformation space. But in all the other cases, you have a rich structure of simple closed curves and measured laminations on the surface, and the deformation space is much more complicated. So in general, for any hyperbolic surface, one gets a cone described by pictures like these as the fiber of the map, and that total space of the fibration is the deformation space classifying these structures. So these are a few of the examples, both that I wanted to illustrate the complexities in trying to define a deformation space and some of the successes in trying to work out spaces. So thank you very much.
Any questions? In that case, can I thank Bill again?